Good morning all. So in today's class, we are going to discuss about the topic DC machines. So in the previous sections, we discussed about the DC circuits and AC circuits. So based on the supply, we are classifying the types of circuits. Likewise, we are classifying the machines, electrical machines into two types. One is the AC machine, the another one is the DC machine. Um, so in this module, we are going to discuss about the DC machines. First of all, we have to know about the types of machines, right? So basically, the machines involved in the energy transfer method. So it helps to transfer the energy from one form to the another form. An electrical machine which deals with the energy transfer either from mechanical to electrical form or from the electrical to mechanical form. This process is called as electromechanical energy conversion. An electrical machine which converts mechanical energy into electrical energy is called as an electrical generator. So the vice versa, that is the machine which converts an electrical energy into mechanical energy is called as electrical motor. Such electrical machines may be related to an electrical energy of an alternating type, which is called as the AC machine, or may be related to an electrical energy of direct type, that is direct, can be said that. No? So the electrical energy of direct type is called as DC machines. The DC machines either it is classified again it is classified as DC generators and motors. So based on the conversion, the mechanical power input power to DC electrical power is called as DC generator, and the electrical power into mechanical power is called as DC motors. So first we have to know that the construction of both the types of machines are same. So, what is the principle behind the operation of this DC machine means? An electrical generator is a machine that converts mechanical energy into electrical energy, as already we discussed. So, it operates based on the principle Faraday's law of electromagnetic induction. We know that the Faraday's law states that whenever magnetic flux is cut by a conductor, an EMF is induced, which will cause a current to flow if the conductor circuit is closed. The direction of that induced EMF is given by the Fleming's right hand rule. The EMF generated is classified as the dynamic and the static one. The basic requirements for dynamically induced EMF to exist are a steady magnetic field, a conductor capable of carrying current, the conductor to move in the magnetic field. So these are the basic requirements which are all need for the dynamically induced EMF. The working principle of an DC machine which acts as a generator is explained with the help of a diagram. So this is the diagram. So from this diagram, you can clearly understand that there is a two poles, that is magnet north and south pole we are placing. So in between that, first I'm telling the concept and then we will go through the slide itself. So generally magnetic field will be produced in between the two magnets. So when we are placing the coil in the magnetic field, the flux will get cut. The flux cuts when the coil rotates from its position, that is change its position. At that time the flux will get cut. So when the flux changes, that is will get the flux cut means it changes from one position to the another. So when the flux changes, there is an induced EMF. That induced EMF is received as an output in the form of a current. So this is the basic principle behind the operation of the DC generator. Here the magnetic field is produced between the north and south pole. So the coil which we have placed is named as A, B, C and D. And then we closed that coil too. Okay. Now go to the previous slide. As per the previous slide, it shows a steady magnetic field as produced by the pole pieces of magnet north and south, as I said already. So north and south pole is there. So between that, a steady magnetic field is produced. A single turn coil ABCD is placed in the field, which produced between the pole pieces. The coil is rotated by means of a prime mover. So that rotation is called as a mechanical energy. So the type of as we already discussed that a generator which helps to convert the mechanical energy into electrical energy, right? So what type of mechanical energy is given as input to the generator? Means there are various types of mechanical energy, right? Rotation, push, pull, otherwise force, So these are all a mechanical energy. So any one form of mechanical energy is given as input to the generator. So here the mechanical energy input is the rotation. The coil is rotated by means of a prime mover. That rotation is called as a mechanical energy, that is input to the generator. Thus, as per the Faraday's law, an EMF is induced in the coil. Such an EMF is basically alternating. The bidirectional induced EMF is made unidirectional using the commutators. So this is the diagram as I already we discussed. So this is the basic principle of DC generator. Now we have to concentrate on the construction of that DC machine. So why we are saying that construction of a DC machine means um, based on construction, both the DC generator and motor is same. Based on construction, it is same. So we are generally saying that the construction of a DC machine. So whether the machine is DC generator or motor, the construction basically remains the same. For the satisfactory operation of a DC generator, it should consist of a stator and the rotor. So which is very, very important part in the machine, DC machine. The stator accommodates the yoke, main field system, and the brushes. The rotor has the armature and the commutator as its main parts. So these are all the main parts which are available in the DC generators. So a cross-sectional type of a typical DC machine is shown in the slide. So this is the cross-sectional view of a DC machine. So in this diagram, you can see where the shaft presents, where the brushes, field poles, yoke, field windings, armature conductors are where it is present, and you can see. So this is the construction of a typical DC machine. So see, it has poles. That is, the winding is the coil is wounded over the poles, and about the yoke, field windings, armature. So we are going to study the purpose of, that is, function of the each part. Okay. The first, the main parts are magnetic frame or yoke, pole cores or pole shoes, pole coils or field coils, armature core, armature windings or conductors, and the last one is the commutator. So what is the purpose of the yoke? So what is the function of the yoke? Why we are placing this? And the outer frame of a DC machine is called as yoke. It is made up of cast iron or steel, which is made up of cast iron or steel, which helps to protect the system. So it not only provides mechanical strength to the whole assembly, but also it carries the magnetic flux produced by the field winding. So this is the diagram which helps to understand the form of the yoke, how it is placed and all. Then poles and pole shoes. Poles are joined to the yoke with the help of bolts or welding. Then they carry the field winding and pole shoes are fastened to them. Pole shoes serve two purposes. So it performs two functions. So what are they means? They support field coils and separate out the flux in air gap uniformly. So what about the field winding means? They are usually made up of a copper. Field coils are former wound and placed on each pole and are connected in the series. The field windings always connected in series. So this is the way how we are placing the field winding in the system. Next, the armature core. So this is the diagram which shows the armature core. It is the rotor of the machine. Usually it is cylindrical in shape with the slots to carry armature winding. The armature is built up of thin laminated circular steel discs for reducing the eddy current losses. So this type of material which helps to reduce the eddy current loss will improve the efficiency of the machine also. So we have to select the appropriate material for constructing a part which will helps in the output of the that is improvement in the output of the machine. The armature of a DC generator permits rotation for mechanical generator action, houses conductor in which EMF is induced. It provides the slow reluctance path for the magnetic flux. So these are all the function of the armature core. Then armature winding. The armature core are provided with the slots made up of same material as the core, to which the armature winding made with several turns of copper wire distributed uniformly over the entire periphery of the core. The construction of this armature winding is basically of two types. One is wave winding, the another one is the lap winding. The wave winding means the number of parallel paths formed between the armature terminals is 2 irrespective of the number of poles. Whatever may be the number of poles presented in the DC machine, the number of the wave winding A must be equals to 2. But in case of lap winding, it is somewhat different. Here the number of parallel paths is equal to the number of poles of the particular machine. So we termed that capital A, that is number of parallel paths, is equals to P, number of poles. So finally the commutator. The function of commutator is to facilitate collection of current from the armature conductors and converts that alternating current induced in the conductors into unidirectional current. The commutator is made up of insulated copper segments, so which helps to improve the efficiency. Each segment is connected to an armature coil. The commutator is keyed to the shaft. So what about the brushes means it plays an important role. These brushes are usually made from carbon or a graphite material. They rest on commutator segments and slide on the segments when the commutator rotates, keeping the physical contact to collect or supply the current. Anyhow, we are giving the mechanical energy as input, that is rotation with the help of prime mover to the DC generator. Finally, we are receiving the electrical energy as an output, that is the current, with the help of this commutator and the brushes. Bearings are used for smooth running of the machine. So there is an EMF. So finally, we said that the EMF is induced in case of the DC generator. So the EMF equation of a DC generator, these are the terms we are using to derive the EMF equation of the DC generator. So the capital P, the number of poles in the generator, flux per pole in Webers. Z is the total number of armature conductors. A is the number of parallel paths, as already we said. If the wave wound armature winding is placed, then parallel paths is equals to 2. If the lap wound armature winding is placed, then the number of parallel paths is equals to number of poles. So n is the speed of rotation or armature, E, which is mentioned revolutions per minute. So Eg is the induced EMF across the armature terminals. So this is the equation which helps to understand the generated EMF of the DC generator. So according to the Faraday's law of electromagnetic induction, the average EMF induced in one conductor is termed as d pi by dt. So the flux cut by the conductor in one revolution is number of poles, that is capital P into pi. Then dt is the time taken by the conductor for complete one revolution, 60 by n. Finally, we get the average EMF generated in one conductor is equals to P pi by n. P pi n by 60. Then we have to replace the number of parallel paths. That is the number of conductors connected in series in one parallel path is equals to Z by A. So EMF generated EG is equals to P pi N Z by 60A. So this is the EMF equation. There are basic problems which deals with the EMF generation. So these are all the examples for that problem. We have to substitute the values in the EMF equation, then we can receive the generated EMF amount. Okay, thank you.